A more or less complete polarization of light is observed in many circumstances. The polarization of light, scattered by the atmosphere, at 90 degrees to the Sun, is highly polarized. There is a slight polarization of the light reflected by the Moon. These phenomena involve refraction, or total reflection. On the other hand, the same is not true for the strong polarization of the coronal K layer of the Sun and for the partial polarization of stars. The reflection on electrons can, in no case, be assimilated to a vitreous reflection, and the polarization of stars does not involve reflection. The Sun's magnetic field is considered to act directly on electrons to cause light to polarize. In the case of stars, the polarization, generally parallel to the plane of the galaxy, would result from the orientation of the sidereal metal dust by the magnetic field in the arms of the galaxy. The purpose of this video is to provide a unique explanation for these two exceptions, and to present the experiment performed to highlight a similar polarization case, the polarization of the coronal K layer of the Sun in the plane of the galaxy. The observation of the coronal K layer demonstrated this additional polarization on December 14, 1996. The observation in February 1997 confirmed this observation. The device used is essentially made of a diaphragm tube, equipped with a photomultiplier, fixed on an equatorial mount. The right ascension motor was not used. A diaphragm box, the smallest of which has an opening of 0.3 mm, is attached to one end of a main copper tube 40 mm diameter and 1 m long. The main tube is coated on the inside with a layer of anti-reflective paint, and has in its middle part a series of about 10 1 cm long wads of black polyurethane foam, pierced with a tubular orifice 2 mm diameter in the axis of the main tube. An aluminum secondary tube, 5 mm in diameter, mounted in 2 ball bearings, is inserted axially at the other end of the main tube. The inner end of the secondary tube carries a diaphragm of 0.3 mm diameter as well. The outer end carries an analyzer. The secondary tube is rotated by a belt connected to a motor via a flywheel. The opening of the diaphragm tube is 2.5 minutes. A reticulated optical sight, equipped with a solar filter, is attached to the main tube. The geared motors, used for the measurements, turn from 0.75 revolutions per minute to 3 revolutions per minute. Measurements were made using an ordinary tungsten wire halogen lamp, at distances such that the signal matches the calculated value for the K layer. The measurements were taken with a voltmeter. Sky blue gives a maximum output voltage of the photomultiplier of 25 to 30 millivolts at 90 degrees from the direction of the Sun. The order of magnitude of this value is in accordance with the calculations which led to the choice of the photomultiplier. The polarization reaches over 80%. The slight rise of the curve results from the motion of the Earth. A first measurement of the signal, given by the K layer, was carried out on December 7, 1996. The Sun was hidden from December 8 to 13. A westerly wind cleared the sky, and on the morning of December 14, 1996, a light easterly wind dried the air, It is likely that conditions were ideal for the 2 hours of the morning when measurements are possible, given the situation at the observation post. On February 22, 1997, conditions similar to those of December 14, 1996, arose after several rainy weeks. It should be noted that the verification tests without analyzer, carried out in the meantime, required its removal and it was not glued in the same position, so that the maxima do not occur at the same angles as for the measurements of the December 14. As the electron density of the K layer decreases with distance from its surface, attempts have been made to start aiming at a point so close to the surface of the Sun that does not give a photomultiplier signal greater than 1500 millivolts. The telescope makes it possible to estimate that the corresponding distance to the surface of the Sun does not exceed 1/5 of the solar radius. Recording is stopped when the variation is less than 1 millivolt. In all cases, the very rapid drop in the signal in the area between the surface of the Sun and a distance of 1 solar ray does not allow the use of the values recorded. In fact, the K layer is moving in front of the diaphragm tube, since the frame is fixed. The curves obtained were corrected for a decrease in illumination inversely proportional to the square of the distance from the surface of the Sun, measured by the position of the analyzer. The start of each measurement does not occur at exactly the same distance from the Sun. The curves have been shifted accordingly, and the measured voltages have been corrected to correspond to a brightness of the same order of magnitude. The average of the 3 measurements of December 14, 1996, clearly shows a frequency of 4 extinctions per 360 degrees revolution of the analyzer. The K layer of the Sun, therefore, has 2 directions of polarization, which have a deviation very significantly less than 90 degrees, according to the curve of the averages of the measurement. The measurement curve of February 22, 1997, shows the same extinction frequency and the 2 directions are at approximately 70 degrees. The polarization of the Sun's K layer is well known and corresponds to its equatorial plane. However, this experiment made it possible to detect a second direction of polarization. This direction is approximately 70 degrees from the equatorial plane of the Sun. Now it turns out that this angle is very close to that made by the plane of the galaxy with the equatorial plane of the Sun. Indeed, the right ascensions of the center of the galaxy and of the Sun, respectively, of 192.5 degrees and 15.41 degrees, are practically in opposition. The angle between their directions is therefore practically the complement to 180 degrees of the deviation of their declinaisons, that is, 180 degrees, minus 27.13 degrees minus 8.86 degrees equal 161.73 degrees. As the extinction of polarized light occurs twice per turn of the analyzer, the angle between 2 successive polarizations, related to the Sun and the galaxy will be 161.73 degrees minus 90 degrees equal 71.73 degrees. The magnetic field of the galaxy is totally negligible at a distance from the Sun. It can in no case be the cause of the second polarization. The observed polarized light comes from the Sun, which is reflected by the electrons of the Sun's K layer. Such a reflection could only give one direction of polarization. However, The galaxy, like the solar system, are animated by angular momentum. This similarity supports the explanation offered here. It is about fluid mechanics. This science is very little taught and, most often, poorly understood. A lumpen science, a sub-science, in the words of Albert Einstein himself, who, moreover, in his paper dated 1926, on the origin of the meanders of rivers, wrote that, a static pressure difference generates a momentum. This is obviously a total ignorance of the very foundations of fluid mechanics. Only a total pressure difference can generate a momentum. From the point of view of fluid mechanics, the cosmos is a fluid, composed of particles in Brownian agitation. To simplify, it is assumed that the friction is negligible. The cosmos is a perfect fluid. It is compressible, because it carries waves, light and other waves. Ignorance would point out that it is a Newtonian fluid, which is pretty stupid, since friction is neglected. The fluid of the cosmos has been called ether since the Greek philosophers. This fluid ether is obviously the seat of flows. The only one of interest here is the flow to a well. Applying Hamilton's principle, the flows of a fluid towards a well are not stable. They turn. This is evident in water and in the air, but also applies to the ether in the cosmos. These vortices, in perfect fluid, have a tangential speed proportional to the inverse of the distance from the center of the well. This is the result of the Lagrange equation. This is not the case with Kepler's laws. The tangential speed must be proportional to the inverse of the square root of the distance. The Lagrange equation is related to energy, while there is a very simple explanation. If the particles of the cosmos ether are animated, not only by linear Brownian motion, but also by angular momentum, then the principle of equipartition exactly doubles the energy term in the Lagrange equation, whose solution is then exactly a tangential velocity proportional to the inverse of the square root of the distance to the center of the well. However, in a perfect fluid, the rotation of the fluid in the vortex exactly compensates for the rotation around them of the fluid particles. This flow is irrotational. This is not the case in the ether. The energy term is doubled. The vortex rotation requires an input of energy. It can only come from the angular momentum of the ether particles. The rotation of the vortex absorbs part of the angular momentum of the particles of the ether of the cosmos. So galaxies do not respect Kepler's law. Their size causes a significant decrease in the angular momentum available when approaching their eye. The flow of ether in the plane of galaxies therefore occurs ultimately without angular momentum, as for perfect fluids. The tangential speed changes from 1 on the square root of r to 1 on r, as it approaches the eye of the galaxies. It varies very little over a long distance. The angular momentum of the ether particles of the cosmos has an interesting consequence. During the impact of two of these particles, the momentum is transmitted, according to the laws of Descartes. This transmission takes place by elastic deformation of the particles of the cosmos. The elastic deformation of the particles of the cosmos prevents the sliding of the particles on each other due to the flattening of the parts in contact. During the oscillations of electrons, they transmit not only their momentum to the particles of the cosmos, but also their angular momentum. Angular momentum can only be transmitted transversely. This characteristic explains the transverse properties of light. Each wave train is polarized in the direction of the angular momentum of the electron emitters. In the K layer of the Sun, containing electrons, if the angular moments of the electrons are cancelled in one direction, the light reflected by that layer of electrons will exhibit an angular momentum lack of the cosmos ether particles. This phenomenon is the reverse of polarization, but the observation of the phenomenon by an analyzer will be the same. The Sun and the galaxy must, therefore, have an angular momentum lack in their respective equatorial plane. This is what has been observed. In order for an angular momentum lack to occur in the equatorial plane of the Sun, the cosmos ether must revolve around the Sun at a speed sufficient to cause a gradual cancellation of the angular momentum of the particles of the ether perpendicular to its equatorial plane. This phenomenon also explains why planets very close to the Sun, such as Mercury and Venus, do not exactly follow Kepler's law. The angular momentum of the particles of the cosmos is totally cancelled in the direction perpendicular to the plane of the galaxies. As a result, the light will be polarized in this plane. The Sun is obviously close to the main plane of the galaxy, and the angular momentum of the particles of the cosmos is therefore also cancelled near the Sun in this plane, in addition to the cancellation of the angular momentum in the equatorial plane of the Sun. The double polarization of the K layer of the Sun, in its equatorial plane, and in the plane of the galaxy, is explained by the lack of angular momenta in these planes.